We are all used to our decimal number system where we regroup by 10. But you don't always have to regroup by 10. You can regroup by 2, that's known as binary, or 16, known as hexadecimal, 5, 7, literally any number that's 2 or more. We can regroup by, and that will form a number in a different base. By looking at that, we're exposed to a completely different view of numbers. And we're about to take a peek into that today. So what does a number in base n mean? Well, you can write it like this over here, but that probably won't make sense. So let's understand where our place value system comes from in base 10 in the first place. For example, we've got a number 3, 6, 7. And this in base 10 is 3 times 10 squared plus 6 times 10 plus 7. That's just our base 10 representation. So in base 10, it's equal to this. Now, what if that same number, but we're in base, let's say 8 this time. In base 8, this thing over here will be equal to 3 times 8 squared plus 6 times 8 plus 7. So instead of multiplying by 10 for every new digit, it's multiplied by 8. And that's essentially what bases mean. And these bases are very common and useful in math competitions especially. By the way, if you want more of an introduction to bases, I have another video on my channel. You can check that out. I cover all the fundamentals in way more detail. But for now, let's take a look at some cool examples. The base 9 representation of the number n is 27006000052, and that's in base 9. They wrote 9 here so you don't get confused as a digit. What's the remainder when n is divided by 5? So let's write this like we would in base 9. We've got 2 here, but then we've got 5 times 9, right? That's this digit, plus 0 times 9 squared, plus 0 times 9 cubed, plus a bunch of zeros we don't care about. First of all, let's write 9 to the 0, 9. Let's just write the position of all the digits so we can get an idea of what power of 9 we'll have to multiply by. This is a units digit. Let's give it 0 because we're multiplying 2 by 9 to the 0. This will be 1, then 2, then 3, 4, 5, 6, 7, 8, 9, and 10. So these are all of the position of all of our digits. And this is to evaluate this expression in base 9, we simply multiply each digit by 9 to the power of its position number, and we add them up. So let's write what this will be equal to in base 9. It is 2 times 9 to the 0 plus 5 times 9 to the 1 plus 0 times 9 squared plus 0 times a bunch of things, all the way until 6 times 9 to the 6 plus 7 times 9 to the 7, or 9 to the 9, plus 2 times 9 to the power of 10. Okay, so then what do we do to find the remainder when it's divided by 5? Well, if you watch my videos on modular arithmetic, you'll know how to deal with this. The key here is that 9 mod 5 is -1. Should definitely check out the modular arithmetic video. 9 is congruent to -1 mod 5. So this is 2 times -1 to the power of 0 plus 5 times -1 to the 1, and so on, or not so on. Let's write all of them out. Plus 6 times -1 to the 6 plus 7 times -1 to the power of 9 plus 2 times -1 to the 10. Now this looks a lot cleaner than having 9 to the power of. Anyways, it's not like I'm going to multiply 9 10 times in this video. So -1 to the power of 0 is 1. So this becomes 2 plus 5. -1 to the 1 is -1. So 2 plus -5 plus -1 to the 6 is 1. So plus 6 plus 7 times -1 to the 9, which is -1, -7, plus 2 times negative 1 to the 10, which is just equal to 2. So from here, what we can see is if we add all these up, we get 10 minus 12 is negative 2. So this is negative 2 mod 5, which is the same as 3 mod 5. So therefore, it leaves a remainder of 3 when divided by 5. And that is our answer. Let's summarize. So we first converted to base 9. Then we saw the mod pattern over there and substituted that here. And then finished with basic modular arithmetic. Let's take a look at another cool example. Find the 3-digit positive integer a, b, c, whose representation in base 9 is b, c, a, where a, b, and c are not necessarily distinct digits. What does base 9 mean for this case? b, c, a, base 9. What is that equal to? That's 9 squared b plus 9c plus a. Let's simplify that. 81b plus 9c plus a. But we also have it's a, b, and c in regular decimal, which is 10. So a, b, c base 10 is a times 10 squared, which is 100, plus 10b plus c. And the cool part here is these are equal. They're the same number. So let's see what we get. We have 81b, that's a plus 81b plus 9c is 100a plus 10b plus c. Let's subtract. We can move all the terms. We have 99a minus, or 99a on this side is equal to 81b minus 10b, so 71b plus 9c minus c plus 8c. So what do we do from here? Well, the key thing here is we're trying to find a 3-digit positive integer that satisfies this condition here. 71b plus 8c is 99a. So how do we solve this? I mean, there's going to be a lot of possibilities, and it's kind of like a diophantine equation, which is an integer equation that we explored in the previous video of the series. So the key thing here is sometimes it's helpful to take mods. If you remember from the diophantine equation techniques, what mod should we take here? Well, the key thing here is we can take mod 71. So let's take mod 71 from here. We end up with 8c equal to 28a mod 71, because 71b is a multiple of 71. So from here, we can divide out by 4 to get 2c is 7a mod 71. And does this mean 2c has to be equal to 7a? Well, if 2c is not equal to 7a, then 2c can equal to something like 71 plus 7a, or 2c plus 71 is 7a. But the key thing here is that they're all digits from 0 to 9. So this isn't possible. 7a is never going to be equal to 71, even if it's the largest possible digit, 9. So we must have 2c equals 7a. C equals 7, a equals 2. Let's plug it back in to our original equation to solve for b. Well, 8c, that's 56, equals 99a, 198, which leaves plus 142. 71b is 142, b is 2. That's 227, the final answer. Let's summarize. First, we look at the base 9 and 10 representations. Then, we substitute those over here and get a diophantine equation. We take mod 71, because the key thing here is we're trying to eliminate those terms. So 99a mod 71 is 28a, and then we end up with a simple equation, solve with mods, get our answer, and celebrate that we have our answer done. 227. That was a cool problem with mods, but let's take a look at another problem here. A base 10 3-digit number n is selected at random. Which of the following is closest to the probability that the base 9 representation and the base 11 representation are both 3-digit numbers? Well, what does it mean for a base 9 representation to be a 3-digit number? Well, for base 9 to have 3 digits, what does that mean? Well, notice that this can be anything from 0 to 8. We cannot have a digit 9 in base 9 because then we would just regroup and form a 10. So there's no 9 in base 9 because that would just be 10. We regroup. It's just like why we don't have a digit 11 in base 10. Because we don't have a digit 11. It's 10 and then 1. So, 3 digits, base 9. First of all, what's the minimum possible value of such a number? Well, the minimum possible value to regroup 2 times. Well, notice how this number, that the number over there in the hundredths place is always multiplied by 9 cubed. So, let's call this number a. The value here would be a times 9 cubed plus something else. So it can't have 3 digits unless this a is at least 1. And so the minimum possible value, such that it's a 3-digit number, or this should be 9 squared, because we go 2 back to get to the units place. So 1 times 9 squared, the minimum possible value, such that this becomes a 3-digit number, is 81. And 81 in base 9 is 100. Cool. What about the maximum? Well, the maximum would have 3 digits, with 3 digits, with having each digit maxed out. So the maximum value for each digit is 8, 8, 8. So 8 plus 8 times 9 plus 8 times 9 squared. And we can do this 2 ways. You can use the geometric sequence formula if you want, but I'm just going to add it up here. 8 plus 72, 80, plus 648, and that will simplify to 728. So maximum value, 728, which forms 1,000 in base 9. Okay, cool. What about base 11 being 3 digits? It's something very similar. So the maximum, what is the maximum possible value for having 2 digits in base 11? Well, we would have each digit maxed out. So this would be a 10 digit, and this would be a 10 digit. And by the way, I haven't mentioned, but in base 11, we generally call this 10 digit an A. So the 10 digit is just an A. So this is 10, this is 10. And it's not 10 the number, it's 10 the digit. So that's why it's called A. So AA. The maximum value for that is 11, or 10 times 11 plus 10, which is 120. So that's the maximum possible for 2 digits. The minimum possible for 3 digits is 1 more, because as soon as we add another 1, then we have 100, which is 121 in base 10. So 100 base 11 is 121 base 10. So the minimum possible value of a number such that it has 3 digits is 100 base 11, which is 121. So 121 is the minimum to get 100 base 11. What about the maximum? The maximum will, again, it will have all 3 digits maxed out at A, which is 10. So 10 times 11 squared plus 10 times 11 plus 10. That's 1210 plus 110 plus 10, which is 1210 plus 120, which becomes 1330. So the maximum is 1330. So, therefore, how can we find our answer from here? So, from here, what we can do is see that the range of numbers that actually works is going to be the intersection of these 2 ranges. So for it to be a 3-digit number in base 9, it has to be from 81 to 728. But in base 11, it has to be from 121 to 1330. So for both of these conditions to be true, that the base 10 and the base 11, it has to be from the range 121 to 728. And these are all 3-digit numbers in base 10, so we're good. How many such numbers are there? There's 608 numbers. 728 minus 121 plus 1. 608. And so what is the closest to the probability that n are both 3-digit numerals? Well, that right there, that will just be 608 divided by the number of 3-digit numerals. How many 3-digit numerals are possible? Well, there's just going to be 900 3-digit numerals. So 608 by 900, and let's just cancel, because we've got a bunch of common factors here. Let's first move this little here. This becomes 152 over 225, and can we maybe simplify this just a little bit more? No, we can't simplify this a little more, but the problem was saying that which is closest, and we can see that this is about 150 over 225, which is about 2/3. And the question was showing to the nearest tenth, so to the nearest tenth, this is 0.7. So essentially, the main point of the problem was just finding this, and the rest was easy if you had the answer choices on an AMC. So we just approximate this to be about 2/3, which is approximately 0.7. So it's closest to 0.7. So therefore, as you can see here, let's summarize. We looked at the possible values, base 9 and base 11. We took the intersection of those ranges, and these ranges that we found using our regular base 10 information, and then we found the number of values and divided. Pretty cool problem. It's a standard trick that's useful. So here's another cool concept. Now remember at the start of the video, I said decimal system. Well, bases have decimals too. Now you might be really confused. What is decimals and bases? What is 0.1 base 3? Let's take a look at that. Well, first of all, what is 0.1 base 10? That's just 1/10. Now, why? Why do we divide by 10? Because 10 is the base. So what about 0.1 base 3? As counterintuitive as it might sound, this is a third. Yes, it's a third. 0.1 is a third. Now you can always say that, because if you don't know which base is specified. So 0.1 base 3 is a third. What about something like 0.25, but in this time it's base 5? Well, this would be 2 by 5 for this digit, plus 5, or this is actually not possible. Let's say it's 0.24 base 5. So then we would have 2 over 5 to the power of 1 plus 4 over 5 squared, because this is 2 decimal places. Just like if we had 0.24 base 10, this would be equal to 2 over 10 plus 4 over 10 squared. So this we can evaluate to be whatever, but the point is it's very similar to decimals, how we use them in base 10. Okay, that's a cool thing, but now let's solve an actual AMC problem that uses this. For some positive integer k, the repeating base k representation of the base 10 fraction 7 over 5/1 is 0.23 bar k. Now you might be confused. So now we have decimals in base, but we also have repeating decimals? Yes, but don't worry, it's not that scary. So 0.23 base k can be expressed like that. What is this expression in terms of k? Well, this first digit is just 2 divided by k, right? Because we're 1 digit in. The second digit is 3 over k squared. The third digit is 2 over k cubed, and so on. Oh, that seems like it's never going to end. And we're asked to find when it's 7 over 51? How are we supposed to do that? Well, the key thing here is it repeats. Notice how these two terms are the exact same, except that they are divided by k squared. So let's write this as, first of all, let's find a common denominator. This becomes 2k plus 3 over k squared, because we multiply by k to the top and bottom. And this would be plus 2k plus 3 over k to the 4, right? Common denominator. And it keeps going. Now let's pull out 2k plus 3. It's common amongst all the terms. This then becomes 1 over k squared plus 1 over k to the 4, so on. And that is 7 over 5, 1. If that's 7 over 5, 1, then how do we solve for that over here in terms of our equation? Well, this is an infinite geometric sequence, and we know the formula for that. A over 1 minus r. 1 over k squared over 1 minus 1 over k squared times 2k plus 3. That's 7 over 51. Now let's simplify this right term here. It's a little ugly, I'll admit it. So let's multiply k squared to the numerator and denominator. 1, that becomes, numerator becomes 1. Denominator becomes k squared minus 1. We just multiply by k squared to the top and bottom to get a much nicer fraction. Okay, now let's move this to the other side so we don't have fractions anymore. 2k plus 3 is 7 over 51 times k squared minus 1, which is 7 over 51 k squared minus 7 over 5, 1. We're trying to find k, and k, it has to be an integer. Well, so now you can actually solve this quadratic using factoring or quadratic formula or whatever you want. But there's a handy little trick you can use here, actually. So the trick that you can use in this problem here is to see that this term is almost negligible. So essentially we have this is equal to approximately 2k. So approximately 2k is 7 over 51k squared. So approximately we have that 51 over 7 times 2 is 102 by 7. This will be approximately equal to k. And this over here is approximately 15. So now the key thing here is we know approximately what k is. It's about 15. So does 15 work first of all? Well, 15 would result in this side being 33, but then this side would be 7 over 51 times 225. But that doesn't work over there, as you can see, because we need to have, because if you subtract 7 over 50, well, first of all, in this right expansion over here, we factor out 7 over 51 times k squared minus 1. Then this term right here for 15 is 224, 15 squared minus 1. But the left side is an integer. The right side will not be an integer because 7 over 51 times 224 is not an integer. Now, we know 15 didn't work. Now, is there any other nearby values we can maybe try? One that would maybe make the right side an integer? Well, if we try 16, this side becomes 256 minus 1, 255. Aha! This side is an integer, 35. Because 255 divided by 51 leaves 5. So 5 times 7, 35 on the right-hand side. Now the left-hand side is 2k plus 3. So we have that 2k is 32, k equals 16. Aha! It does work after all. So 16 is the answer to this problem. Cool trick, huh? We didn't have to solve that ugly quadratic. We instead knew that it has to be a positive integer, so we just kind of guesstimated just a little bit and found it out. Let's summarize. So first we translated this to our base 10 version. We got this giant expansion. And then we group terms together and we get an infinite sequence that we evaluate with the infinite geometric sequence formula. Then we have a giant quadratic, which you can solve by the boring ways, quadratic formula, factoring, blah, blah, blah. But instead, estimate the integer and then see what the possibilities lie from there. And you can get all these practice problems for free in the free AMC 1012 book. Link in the description, download below. So number theory is a very cool topic, but there's some topics that are just miscellaneous and they're still important to know, like palindromes, chicken McNugget theorem, and many more. And there's some cool problems that don't really fall into any topic, but they're still interesting and fun to solve, like this cool problem here, or even this one here. Let's take a look in the next video.